SwayamPrabha. Digital India. Educated India.
Good morning, students. Let's continue our discussion on the discrete structure analysis and following the finite element procedure. In our previous class, we talked about one-dimensional elements, a system consisting of all one-dimensional elements, and we took them as spring elements, which are equivalent to our truss elements as such, because truss elements taking only the axial loads and together with the axial deformation can be considered to be equivalent to spring. Now let's look at the same truss element to be more practical in the 2D orientation. So in the sense that we have, again, we know that we have a structure here, and we limit ourselves for the moment in 2D, and where there are a lot of elements at different orientations, as we have seen in the last lecture. So what we are trying to do now here is we are trying to derive the element equation. So we are looking at the element equilibrium equations, so wherein we have a truss element in one-dimensional length, that's all, and then we have x and y axis. So this point here, and let's call it as node 1 and node 2. And here, this is now under the action of forces, and because of this forces, so this is going to undergo, so I'll use some other, so this is going to undergo a deformation like this one. This is the displaced configuration. So the node 1 has gone to node 2 here, 1 prime, and 2 has gone to 2 prime under the action of two forces. So this is, we call it as F1x, and this is F1y, and F2x and F2y. So these are the forces. So this is the original configuration, and then under the action of F1x, F1y, F2x, F2y, it has moved to a new position, and let's call this as this displacement here of node 1 is represented by we'll put it as u1 and v1 are the two displacements in x and y directions, and here also we have u2 and v2 for 2 prime. So the movement of 2 to 2 prime and 1 to 1 prime is represented by the displacement components u and v. So what we are saying here is that under the action of these forces, the nodes have gone to 1 to 1 prime. And let's also show that this is at a orientation of alpha. This truss is at an angle of alpha. Okay. And then what we would like to do, keep that in mind. Let's just remove that. So what we would like to do is that we would like to get the relationship between the force components and the displacement components. So we can see that there are 4 force components and 4 displacement components. So we can write the relationship like in a matrix form, like here, and a matrix here multiplying components U1, V1, U2, V2 as F1x, F1y, F2x, and let's so this relationship, and then this relationship is a matrix of 4 by 4, which we write as A11, A12, A13, A14, and like this we fill it up. A23, A24, okay. So this is the 4 by 4 matrix, which we call as the stiffness matrix. So our task is to find out all these 4 by 4 elements. So that means under the action of those forces, so that means that if you know the forces, you can calculate displacements if you know the stiffness. This is called the stiffness matrix. So this can be derived in many forms. So quickly, what we would like to do is that, so we will find out a way. One method is to find out the unit displacement method. For example, if you give unit displacement to this one, for example, if you give unit displacement as an example, we will give that systematically. Say V1 is equal to 1. So this one may be very small. Okay, so it's a small displacement considering the large structure. So that means that these movements here, U1, V1 and U2, V2 are small deformations. So what we have here, so if you give V1 is equal to 0, keeping all others, fixed, in the sense that U1 is 0, U2 is 0, and V2 is 0. So that means that what we are looking at, we have thing like this, and this one, node 1. So V1 means what? So it's a displacement in the vertical direction. So that means that we are giving V1 equal to 1, keeping U1 0. So that means that, and similarly U2 and V2 are 0. So the node 2 stays here and 1 goes to 1 prime, and this is the deformed configuration. So 2 and 2 prime are right here, and 1 has gone to 1 prime. And so that means that this is, of course, the orientation of the element is alpha. So what we are saying here is that if one has gone to 1 prime, it happens only because there will be certain forces. So the forces, that means that there will be forces like this, F1x, Fy, and F2x. Okay. So what we have, F1x, F1y, and F2x, F2y. So these are the forces. Under the action of these forces, so 1 has moved through 1 prime by a unit distance, and 2 remain as it is. So what is the significance of these things? The significance of this one, if you put u1 is equal to 0 and v1 is equal to 1 and u2, v2 being 0, so then what will happen here is that if you multiply this one here with the column here, so it will be simply k12 multiplied by v1 is equal to f1x. So similarly, k2 multiplied by v1 is equal to f1y. k32 multiplied by v1 is f2x. So under the application of this kind of displacements, so this is the relationship, because everything is, the other 3 are 0. So the relationship will finally boil down to this one. So which means that if v1 is equal to 0, 1, then what happens simply, then if you can find out, so what this turns out is that, so k21 will be simply f1x, k22 will be simply f1y, and k12 here. So this is 1, 2, this is 3, 2. So that means that we are able to get these values of second column of k, k12, k22, k32, k42 as simply the forces necessary at node 1 in the x direction and in the y direction at node 1 and x and y directions of node 2. So they are nothing but the k matrix values of the second column. Okay. So let's try to find out for this case. So if you have a unit displacement like this one, what you can see is that this original length of the member 1, 2 has now shortened to a 1 prime, 2 prime. So what is the shortening here? So the shortening here can be found out by projecting this one 1 prime, 2 prime onto the original orientation here, and then so this part will become the deformation here. Okay, so that is the deformation in the length of the element. And how much is this one? So if this is equal to 1 unit displacement, and what is the angle alpha here? So this is alpha. So that means that this is also alpha. So the deformation, shortening of the length, deformation of element. So in the sense that this is, in this particular case, it is a shortening, and this is, if you call it as delta. So this is nothing but, if this is 1, so its projection here onto this one is nothing but 1 times sine alpha. So this is alpha here, and then the opposite side is 1 times alpha. So imagine that this is, now we are calling it as 1, it is really a very, very small deformation, and we will apply all the rules of small deformation so that the shortening of the length is equal to the projection here. So there is nothing else other than this one. So if this is the shortening of the length, then what we have here is that, I'll draw the figure again here, because of the shortening of the length. So, right, so this is okay, because of the shortening of the length. So we say that it requires a force F1 here and F2 here, right? So these compressive forces that are necessary here, F1 and F2 are equal. So how much is that? So this is, we have seen that the stiffness of the element in the axial direction is nothing but AE by L multiplied by delta here, and which is equal to L is the length here and delta is nothing but sine alpha. So we can also see that the original alpha and this alpha are not very much different because these are all small deformations. Okay, so the orientation doesn't change. So this is the force in the truss element. So this is the force necessary so that you can have a unit deformation in the y direction. So if this is so, then since this we are talking about we are talking about 1D. So these forces can be decomposed into x and y, and we know that this is alpha. So what we have here is F1x is whatever you have here, F1 multiplied by cos alpha, and which is nothing but AE by L sin alpha cos alpha, right? So this is F1x, and similarly F1y is nothing but this, but the component is sin alpha, right? So this is in the horizontal direction, so the vertical component is like this one. So we can also say that, as we were saying here, so that means that this is nothing but your K12 and this is nothing but your K22, right? So what about here? So here, exactly the same as this, again the same angle alpha, but they will be in the opposite direction, right? Because the force is acting downward here. The components are just the opposite of this one. So we can, I'll continue here exactly. So here, so that means that F2x is minus AE by L times sin alpha cos alpha, and F2y here is minus AE by L sin alpha sin alpha. So like this, so we are able to get the K1, K12, K22, and this is K32, and this is K42, right? And so similarly, we can also find out all the other members of this one. For example, how do you calculate the first column here? So to calculate the first column here, so this node 1 will have a displacement of 1 unit in the x direction, in the horizontal direction, and find out what is its projection length on the original orientation, and find out what is the deformation, and accordingly you calculate the whole thing, right? So finally, so this matrix here is, we can write it here as it's AE by L multiplied by here, this is here, this is cos square alpha, this is cos alpha sin alpha. Well, this is what we have calculated just now. Maybe I'll just write it down this first. And sin alpha cos alpha, and this is sin square alpha, and this is sin alpha cos alpha with a negative sign, and minus sin square alpha. So the same thing here. So this is cos square alpha, and this is sin alpha cos alpha here. And then we continue here. So you can do the same procedure for the other one, other columns also. U1, B1. So I'm just filling it up for the sake of completion. So you can also see here that this K matrix, this which we call as the K matrix or the stiffness matrix, is symmetric because of the principle of Maxwell's reciprocal principle, and where the matrix elements have to be symmetric in nature. So this is the fundamental thing because of the Maxwell's reciprocal principle. So that means that if you apply a displacement at one point, then the displacement at some other node should be same as the displacement here, and find out the deformation. So here if you take that, so that means that Kij, Kji, Kij, what is Kij? Kij is nothing but apply a unit displacement at j and find out what is the force at I, keeping all other displacements 0. So that should be the same as Kji. Okay, so this is because of the Maxwell's reciprocal principle. Okay, so this is how we can derive the stiffness matrix for a truss element in a general orientation alpha. Okay, so now it's also important that there is another calculating this stiffness matrix in a general orientation from transformation matrix point of view. So here, using transformation method. So what is this one? So what we have is that, so this is often very important and very useful. So this is the xy axis, set of axis, and this is the general orientation at alpha. So what we know is that, for example, if I set up axis here, x prime and y prime, let us say. So then in the direction of x prime, let's say there are displacements here, for example. So the point 1 has moved to 1 prime here. Okay. And you call this as U1, V1. And here we have U2, V2. And what we know here, interestingly, is that the stiffness matrix of the element in its own axial direction we have already derived from the spring point of view. So in the direction of x prime, in the direction of x prime, so in the direction of x prime, then the displacements here will be a projection of this one here in this direction, right? Okay, in the direction of the original orientation, so we have the displacements from here to here, which we call as U1 prime, and here we call this as U2 prime. In the direction of x prime, the deformations are U1 prime and U2 prime. The deformations perpendicular to the orientation of this element does not come into the picture because they will not cause any shortening of or elongation of the element, and it will not cause any force generation. So in the direction of now x prime, so we have let us say the relationship between f1 prime and f2 prime. We can write it as what? So AE by L, which is the K, the stiffness like that of spring. So AE by L is nothing but the stiffness of the truss element in the axial direction, or you can also say that it is spring stiffness. So what is this U1 prime and U2 prime? So U1 prime is nothing but deformation of the node 1 in the direction of the axis of the element. So similarly here U2 prime is nothing but deformation of the node 2 in the direction of x prime. Okay, and what is this f1 prime and f2 prime? So these are nothing but whatever you have here, f1 prime and f2 prime here. So what we are talking here, so we will just write it again here. So we have f1 prime like this, and this is f2 prime. This is f1x, 1y, just like we did it earlier. This is f2x and f2y. This is about the forces, but what about the displacements? So the displacements are u1, v1 in the xy reference direction, whereas we need u1 prime. Here to use it here, so we need u1 prime. So u1 prime, if you want to write, so it is nothing but component of u1 here along the axial direction. So that is u1 cos alpha, as well as the component of this v1 which is perpendicular to this or in the direction of y. So if you want to take its thing, so this is alpha and that is the sine alpha. So you have v1 sine alpha. So similarly here we also have u2 prime. It only depends upon 2. So it is nothing but u2 cos alpha plus v2 sine alpha. So this is regarding here. Okay. So what we have here, we can write in the matrix form. So in the matrix form, we can write it in the sense that if you know U1, V1, U2, V2, you can get U1 prime and U2 prime by multiplying this with this matrix, which resulted from this equation. So this is called a transformation matrix. So you can say lambda so where lambda is the transformation matrix. So that means that using this, if you want to use this one-dimensional equation, so in the place of this, if you write down this lambda times this one, so that means that the displacements are in the original xy directions. Apart from that, so let's also, having got this one, f1 prime and f2 prime, so if you want to, so if you look at this one, if you want this one here, f1x, so f1x is nothing but f1 prime, right? So this is alpha here, it's nothing but cos alpha, and f1y is nothing but f1 prime sin alpha, right? And then we can also write f2x as f2 prime cos alpha f2 prime sin alpha. So this, if you can write it in the matrix form, so this is what we actually need. So the four components in the original xy directions. So we have here so whatever this f1 prime cos alpha, so that's what I'm writing here, and this is f1 prime sin alpha, and this is f2 prime cos alpha, and this is. So if you observe carefully, so this matrix is in relationship with your earlier transformation matrix, which we call lambda, but then this is in the transformation, transpose form. Right? So this is what we have written. And now let's combine everything. So this is what we have here. And so that means that this u1 prime, u2 prime, we will replace by the complete displacements, four component displacements, whereas this we want to pre-multiply with this one so that we get the complete transform thing. So let's write it, maybe we will write it again here. So that equation, let me write it here, f1 prime. So this is AE by L. I can take AE by L common. And this u1 prime, u2 prime, which we have derived earlier, so which we represented by lambda. And here we write u1 v1, u2 v2. So this thing now, we will write it as f1y so this is transformation matrix, transformation matrix lambda, which we just wrote there, transpose, and this stiffness matrix in the axial direction, and this one here, lambda again, So this is another, if you just use the lambda and everything, whatever is there. So if you multiply everything together, this will be simply become cos square cos alpha sin alpha, exactly the same thing as what we got earlier. So if you do this multiplication here, this is exactly what we get. Okay, I'll just write it here. The only upper triangular matrix I'll write, because we know that it is symmetric. Okay, so you can see that using this technique of deriving the stiffness matrix using the transpose of the coordinate system is much more elegant, and then this can be used for further extension of these matrix manipulations of stiffness into 3 dimensions and many other things as well. For example, tomorrow I'll show you how to write it for the bending stiffness, so that also can be transformed into 3 dimensions. So that means that anything thou derived in the local one-dimensional axial directions, so can always be transformed into a general x, y, z directions. So this is a very, very powerful technique, and we can derive this stiffness matrix in a very systematic manner. So the only thing that is required here is deriving this transformation matrix lambda. Once you know lambda, it is nothing but it is lambda times the stiffness matrix in the axial direction multiplied by another lambda. So together with that gives you the stiffness matrix in the original xy direction. Okay, I think we'll stop here and we'll continue in the next class.